Hello, in this video we're going to go over how to prepare ethers and also the types of reactions they can perform. So let's start with how to prepare an ether using an industrial method. So in this method we would first take a primary alcohol and we're going to perform substitution on this alcohol. However, remember that OH is a poor leaving group. Oops. So we need to first convert that into a good leaving group. So let's use an acid. Okay, so now we have a better leaving group. And then we're going to take another alcohol molecule, and that's going to come in and perform an SN2 reaction. And we're going to end up with something that looks like diethyl ether, but we haven't quite finished yet. We need to deprotonate that oxygen, so we'll just use something like water. Okay, and then we have diethyl ether plus an acid. So actually the acid regenerated from the first step, so it acts as a catalyst. Now, there are some limitations to this method. You have to use primary alcohols in order to get that SN2 reaction to occur. So that's one limitation. Another limitation is that you need really high temperatures for this to work. And you need a really strong acid. So the strong acid can be, a hazard for the scientist, and the high temperatures could also be hazardous. Additionally, you can only form symmetrical ethers. So if you wanted to form an asymmetrical ether, this would not be the way you would do it. So again, a lot of limitations here, but luckily a British scientist named Alexander Williamson was able to find a different method of preparing ethers. So we have a whole synthesis named after him, the Williamson ether synthesis. And this was demonstrated in the mid-1800s. So in this method, you start with an alcohol, similar to before. And then we're going to use we're going to use sodium hydride. And the hydride is going to come in and deprotonate the oxygen. All right, and that's going to give us hydrogen gas as a byproduct, but that's okay because it will just bubble off. You'll also notice that we've formed an alkoxide ion. All right, and then in the next step, we're going to use an alkyl halide, and I'm going to put a little quotation mark next to the R group on this alkyl halide because that indicates that we might have a different R group. So remember earlier we drew the ether where one of the R alkyl groups had a little prime or quotation symbol next to it. And that just indicates that we might have a different group. So this could be an asymmetrical ether. All right, so the alkoxide ion is next going to attack that. Oh, whoops, I drew the arrow in the wrong place. I apologize. That's going to attack the carbon next to the halogen, and the halogen is going to leave. Now, you do need to use a primary alkyl halide here in order to perform SN2. Otherwise, you might get an elimination reaction instead. But what you end up with at the end is potentially an asymmetric ether. Now, you could make a symmetric ether as well. That's totally fine. But the main purpose of this synthesis method is to potentially form asymmetrical ethers. And then the sodium ion and the halide that left will form an ionic compound. All right. And I'll just add a little note down below that you can form symmetric ethers too. All right, so let's look at another way to make ethers. So this method is called alkoxymercuration demercuration. So remember previously we learned how to perform oxymercuration demercuration, where we added an alcohol group to the more substituted carbon, and it also avoided rearrangement processes. However, now we're going to do a similar thing, but instead of an OH group, we're going to add an OR group. So let's see what that looks like. So let's recall that for oxymercuration demercuration, if we had an alkene and we added mercury acetate and water, followed by sodium borohydride, we would end up with an alcohol, again on the more substituted carbon. Okay, so now for ethers, we can do a similar process. So let's start with the same alkene. And we're still going to use mercury acetate, but instead of H2O, we're going to use an alcohol. And again, we'll follow that with sodium borohydride. So we're just replacing water with an alcohol. But instead of adding an OH group to the more substituted carbon, we're actually adding the OR group to the more substituted carbon, so that we end up with an ether. So this is another way to make an ether. This method isn't as common just because we are using mercury. And remember when we talked about oxymercuration, demercuration, we talked about how mercury can be poisonous, and it can start to affect your nerves and your mental capacity. So we tend to try to avoid using mercury as much as possible. So we'll just make a little note, not common due to mercury. All right, so let's talk about some reactions that ethers can perform. So in the, let's see, so the one reaction we're really going to talk about is acidic cleavage. And your book does cover another mechanism called autooxidation, but we're not really going to worry about that here. So we're just going to cover acidic cleavage. So this should just say reaction of ethers. Let's see, so we'll talk about acidic cleavage. All right, so we'll start with an ether, and let's just assume that it's an asymmetric ether. And we're going to react this with an acid, where X is either bromine or iodine. So this is a little bit different. Normally we say, oh, you can only use bromine and chlorine, but here we're going to need either bromine or iodine. So what happens first is the oxygen grabs onto the hydrogen from the acid, and that leaves the halide behind, or the halide, I guess, however you want to pronounce it. And then we're going to form a positively charged oxygen. Now, what we also just formed was a good leaving group. So now the halide can come in and attack the carbon next to one of the alkyl groups, and that's going to cause our leaving group to leave. And this is partly why we need the halogen to be bromine or iodine, because the other halogens won't necessarily perform that same reaction. Okay, so next we end up with an alcohol. That was our leaving group. And we also have an alkyl halide. Okay, so we were able to break apart that ether by adding an acid. But there's one more step, or actually a couple more steps. So we're going to add more of our acid, and the alcohol is going to grab onto a hydrogen, leaving electrons behind on the halogen. So now we'll have our alkyl halide, and we protonated our alcohol, and then we have our halide ion. So that halogen's going to come in and again attack the carbon next to our leaving group, which is water. So at the very end, we get an alkyl halide plus another alkyl halide. It just kind of depends on what that alkyl group is, and water. So in this reaction, we took an ether, and then we used an acid to produce alkyl halides. So that can be pretty useful if you're trying to produce specific alkyl halides for maybe another reaction down the line. All right. So I think we'll stop there today, and in the next video, we're going to talk about epoxides. So we'll talk about how to name epoxides. We'll also talk about some characteristics of epoxides, how to prepare them, and then we'll go over maybe some practice problems as well. So I will see you then.